So, ZPhysics, you're teaching, aren't you?
I am a teacher. I'm currently a head of department at Ashton Sixth Form College. By the way, I just really want to say that it's an absolute privilege to be here.
Thank you.
Yeah, I started watching your channel when I was a teacher, probably around 2015. So I've been a long-term subscriber, and it feels absolutely surreal to be here.
Okay, and that makes me feel really old. So we are here at my studio. We've got an OCR paper. You teach OCR, don't you?
I do teach OCR.
And I used to teach it. I enjoyed it. I've also taught AQA as well.
So it's the battle of the exam boards today.
Well, we'll see, shall we? We'll see if there's any competition in it. But really what we're going to look at is some questions from an OCR paper. This one is 2022, and we're going to look at modelling physics, which is the first paper. I didn't actually do this paper, but I heard about it through social media. Because I think a lot of students, I think you found this as well, didn't you, that they found some of the questions quite tricky?
Absolutely. I was teaching that year and I remember students coming out of the exam hall and everyone was talking about the really, really difficult 10th question. So that's the one we're going to be having a look at today. I'm really looking forward to it.
Yeah, so we're going to just look at a couple of questions. So the first one is this one here. Now, personally, I quite like camping, being outdoors.
I like camping too, actually.
Yeah, climbing, stuff like that. So the question, they've got, I suppose it's quite a weird shaped tent. It's just like a rectangle.
You don't go camping in a square tent, I guess?
No, however, luckily for the sake of physics, it makes a lot of the maths relatively straightforward because it's like, I guess it's just modelling this kind of real life thing in the simplest form possible. So we've got a rectangular tent. In actual fact, a lot of you might know I've used a bit of Lego. So if you've already tried it like this, I'll just get my Lego tent.
Everyone loves the Lego that Lewis uses.
It is. And, okay, so I think, although it can be a bit childish, we can use this to kind of try and explain what's going on. So here is the tent just built out of Lego. So we've got wind at a certain speed. It blows at right angles to the shaded side of the tent for 3 seconds. And we've got the density of air there. So the first question was the show question. Now, personally, I like a show question because it's given us the answer. So even if we can't work this out, we have an indication that this number is going to be needed for the second part. And also, I suppose it means that if you've done the physics well, you know that answer you've got is that, and that means you've guaranteed yourself 3 marks. So I quite like a show me question.
Absolutely, the same. If we miss that, we can use that further ahead. Another thing that I spot is that we're given the density. Now, to me, this is always a clue that we have to use density is equal to mass over volume because other formulas for density are just really rare in A-level physics. So that's probably the first thing I would personally write down just to start the question off.
Cool, so density is mass over volume. That's going to be needed potentially. So we've got a speed. It's hitting us at right angles. So for this one here then, I suppose the way I think about it, and I think there's quite a few questions, often to do with flow rate, which are tricky, but it's not really something mentioned in the specification where it says you need to be able to work out maybe the rate of water going through a power shower that's kind of heating it up, or the wind hitting something, or maybe, I think there's another one I've seen about a helicopter and there's like air being blown out. And so, using Lego, this is kind of my approach, basically, is
this is absolutely brilliant to visualize.
Yeah, so if we've got like one side of the tent, it's kind of basically this area. So this is my area of tent being hit by air. But we know that the air is moving. And so in a certain amount of time, say 3 seconds, we've got this volume of air that basically passes sort of into that side of the tent. So I suppose this allowed me, and it's really hard to visualize, isn't it? And as we can see, it's difficult to explain this, but I think with Lego, it's basically saying that we need to know the area of the side of that tent, like this, and then we can think, as time goes on, this whole volume of air basically passes kind of through that region or into that region. So what would be your approach for this then?
I think one of the things that I would really try to do is just visualize what a single particle does. So it's moving at 12 meters per second. So that means that in 1 second, one of those individual particles is going to travel, 12 meters. In 3 seconds, that should cover, well, 3 times that. So what I'm going to really focus on is to try and find the volume that the overall wind is going to create as it's impacting the tent. So we're looking for the mass. So probably the first thing I'll do is just to rearrange for the mass. So I'm just going to say that the mass is equal to density times volume. In fluids, it's really, really useful to just remember that volume is typically expressed as the area multiplied by the length or the height of this kind of imaginary cylinder, which makes the problem really hard to visualize.
Yeah. Cool. Okay, so we know the density because it's given to us. We know the area, or we can work it out because it's just 1.9 times 6. The length, we don't know the length, but I suppose we can think about, because speed equals distance over time, the distance or the length is equal to the speed times time. So I guess we can just put that straight back into there, can't we?
Yeah, absolutely.
And then by magic, some numbers will appear like that. And then we'll put the numbers again by magic into the calculator. That should then give us a number of, there we go, 492.48. And I think this is the thing where to get that mark in the exam, you know, kind of in the kind of exam world conditions, I'd always write down the number on the calculator. And we know that that's like 5 significant figures, which is far too many for the 2 in the question. And that's going to be approximately equal to 490 to 2 significant figures. And then the units would be kilograms. And I think it's this bit here for a show me question that students will get the right answer. They often get the marks anyway, but you need to show that you've actually calculated it yourself and not just, and I know this is what students do when they're not sure, they'll just kind of mess some figures in.
Absolutely, please don't do that.
I mean, it's worth a punt in the exam, isn't it? You know, if you're not sure, put some equations in, put some numbers in. Even if you don't calculate it, say equals that. Is that a legitimate exam tip?
I would probably personally not do that, to be perfectly honest.
If you're desperate in the last few minutes,
why not? Yeah.
But yeah, so this one over here, that wasn't actually too bad. But I think there are questions that come up every so often about like the rate of something moving, and you might know the amount per second, but then you've been given the time. So the first bit, even if you couldn't do that, even if you couldn't get those 3 marks, it doesn't matter because the next part is kind of like starting again. Now, I think this is where it got even more difficult.
Yeah, absolutely. So shall we have a read for the question? So all of this air is incident on the shaded side of the tent and then is deflected at 90 degrees to the original direction. We need to use the information in the first part, so this is really important. Often in A-level physics, the questions that follow tend to use a lot of the information, particularly in show me questions. Even if you didn't score that, you can use the mass to be 490 kg. And we're looking for the magnitude of the force. How do you reckon? How would you approach that?
So I think this one here, I think this is a really nice example of where Newton's second law is important, but often students know or they can recite what Newton's second law is about how the force is proportional to the rate of change of momentum, but it's applying it in a real world situation, which is difficult, isn't it? But I think if you're basically we're trying to find the force, we know things like the mass, we know the speed of it or the velocity, we know the time. There's lots of stuff there that says that the force is going to be equal to the rate of change in momentum. That'd be my first thing. So I'd probably just write it down. So I'm going to do F equals mv over t. Now, I suppose I probably should put delta t, but we know we're looking at the change in time. I suppose I should really put delta mv. Actually, I should put delta mv, shouldn't I?
Yeah, I tend to write little brackets over there
to show that it's the momentum. I've done that really bad. I've explained it badly, but I suppose when I was writing it down, I'd be thinking, we're looking at the change in momentum. Oh, that's not so good, is it?
No.
Okay,
it's totally fine.
Well, I tell you what, I'm going to write that better. So, the force is equal to the change in momentum over time. Okay, That's what I should have said. Now that means then that's going to be equal to the mass, which is constant, times the change in velocity over the time. Okay, so I think that's probably a clearer way to say it, isn't it? Okay, ignore the first part I said. Even us teachers get confused. So that would be my starting thing. How about you?
So one of the things that I would think about is essentially about the change of momentum as well. as the wind is going this way, all of the momentum is going in this vertical direction. Straight after it hits it, it moves into horizontally. So all of that vertical momentum is actually lost, which means that there has to have been an external force, which is really the particles hitting the side of the tent and the tent hitting the particles by Newton's third law. But the really interesting thing here is to think by how much the actual mass changes. So we can look at that kind of delta M, delta T term, which will really, really sort of help us, because we calculated our mass to be, well, 490 kg. We could probably use the either this one or this one will give us the marks. So this would probably give us what? Which one should we use?
I reckon I'm going to go for my calculated value. So I'm going to go for 492.48.
492.48.
But you get the marks even if you didn't get that and you use 490, you'd still get the marks, because it's not about the numbers, it's more about the method. Can you approach this? And the numbers are just there to sort of really illustrate it. So that's the mass, but that's the mass in 3 seconds, isn't it?
Exactly right.
And I think that's the thing that it's not that clear. So so that's the mass. The change in velocity then.
So the change in velocity in this direction, once again, we can even call this the y direction. Well, that's going from 12 meters per second to 0, isn't it? So we can just write that our change in velocity is just going to be 12.
Yeah, that's good. Yeah, so that's the change in velocity. That's the mass of air that hits it in 3 seconds. So it's going to be changing over a time of 3 seconds.
Yep.
So it's just divided by 3 or 3.0. So this is equal to 1,969.92. Again, 2 significant figures I think is appropriate. So that number to 2 significant figures would just be 2,000.
2,000 newtons hitting the side of that tent. That's quite a lot, isn't it?
It's a lot, but then it's a windy day, and I guess if you think about when it's really windy, the tent can be blown away or be affected by that storm or something like that.
Not sure I fancy camping with 2,000 newtons.
No,
hitting that tent.
Not at all. It doesn't sound very nice, but I've spent a few nights at altitude, suffering, thinking, why am I here? So okay,
we need a video for that.
Maybe. So that one there, I think when you realise that this is applying Newton's second law, it's actually relatively straightforward, isn't it? And
I think the more experience you have with questions like these, you tend to spot these. So if you've solved a question which is similar to this one, your brain just automatically goes into that mode, thinking, okay, I've done a very, very similar question before. I know exactly what to write. I'm going to start with F is equal to delta P over delta T. And that just saves you quite a lot of time in the exams.
Yeah, and also I suppose thinking about how with things like momentum, the direction is important, and how, in the y direction, if we're not conserving momentum, there must be an external force, and that force is provided by the side of the tent. In the horizontal direction, we're still going to conserve momentum, and so just as much air goes to the left as it does to the right as it goes around it. So this, momentum is conserved, I suppose, but it's just being aware of drawing on your diagrams, adding stuff to them to make it easier to look at. Okay, so the next one is part B. So I think that part B, as soon as students started reading it, it didn't look that bad. But then they saw the 6 marker, they saw some lines here, and they saw there was a whole page for them to kind of complete their answer. Now, personally, I like doing the maths and actually writing down sums.
I love maths.
Yeah. Stuff like this fills me with terror, but actually... I suppose,
feel the terror from the 20 meters per second wind. That's pretty extreme.
That's pretty extreme, yeah. But so actually, what is nice though is that they do have some numbers. So numbers and quantities are good. And maybe one way to think about a 6 marker is it's not one 6 mark question. It's 3 2-mark questions. And if you break it down to thinking, well, can I do a 2-mark question? Yeah. Can I do another 2 marker? Can I do another 2 marker? That's maybe a way, although it's the same question, it's like trying to break it down into more manageable kind of bits. So
completely agree.
So let's think about maybe the first 2 marker within this. We've got some numbers. Basically at 20 meters per second, the ropes break. What could we do to make the ropes or the tent strong enough to stand a wind which is going at 40 meters per second? So I suppose the first thing is we know the wind's going faster, it's going to be a bigger force, but can we quantify that force, bearing in mind they've given us some quantities? So we'll just work on some paper just to kind of do this. So I'm going to pass over to you, right? Zelia, how do you do this? So what would be your approach to looking at the size of that force?
Oh, I really love a good momentum question. So let's have a look. I'll probably play around with some equations. So the first thing that I notice is that essentially this number here doubles. So we know that F is equal to delta P divided by delta T. Okay, well, what's going to happen to each of the terms in the equation that we've actually used before?
Yeah.
So the mass itself, what we found out in the previous part right over here, was that the mass was really proportional to rho A L, but L really depends on the speed. So the higher the speed, the more mass will hit the tent in 3 seconds. So, well, let's just quantify this. M was equal to rho A, and then multiplied by the length of that cylinder, which was Vt. Now, the change in speed was just delta V, so you're actually going to get a factor of V squared because the speed in that direction goes from 12 to 0.
So it's effectively V minus 0, which is still V. Yeah, so that's right, we've got that. So, okay, so looking at that then, this basically tells us that the force is proportional to the density of the air, depends on the area of the side of that tent. We've got V squared, and then we've got like the T, but they can sort of cancel, don't they? So really, the force is going to be proportional not to the velocity, but to the velocity squared.
I think our tent might be in trouble with that proportionality factor.
Yeah, so, yeah, sorry. Yeah, so with that factor then, what happens when we go from 20 to 40? What's going to happen to the size of the force?
Oh, well, let's have a look. So if this factor here is doubled, and that's kind of a typical mistake sometimes in A level. If you were to double this factor, then you have to square the factor itself as well, meaning that the force will actually quadruple. So the new force will actually be, well, let's call it 4F.
Okay, so I think that's an important step, which I think looking at we've got the benefit of hindsight. We did have a look at the examiner's reports, and I think that's something the examiners mentioned.
Yeah, absolutely. If I remember correctly, they mentioned that quantitative answers to this question were actually rare, and I think this is really the key to this question.
Yeah, and also, if you're watching this, you'll probably go, yeah, that all makes sense. All of you could have done that, and that means that you've all got that, or potentially you've all got the ability to get those first 2 marks. It's just writing down, some of the simple equations from physics, and that tells you that if you were to double the velocity, we quadruple the size of that force, and that's maybe a couple of marks potentially in that question when you've kind of packaged it up nicely. So basically, we've doubled the force. So how can we then minimise the effect on the tent? I thought there were 2 main factors. One of them was about the area of that tent, and that kind of comes from up here, doesn't it? Mm-hmm. So we know that the force is going to be proportional to the area. Now, if the force is going up by a factor of 4, that means we need to make the area of that side of the tent 4 times smaller. I suppose I could do that in Lego, couldn't I? We could sort of, we could like adjust it quite easily. But the reason that you've got mountain tents which are quite small and low to the ground is because you don't have like a 6-foot high tent at the top of a mountain. You have a really low tent, so you don't have such a big surface area hitting the wind. And actually, I suppose explain that nicely gets you the marks, doesn't it? Yeah,
absolutely. You can probably find a relationship between the component of the force and the angle, we can call that potentially theta, in an exam situation. The other thing that you could potentially do is literally just strengthen the ropes. There's one more thing which I noticed when I was looking at the question, which was just here. And it mentions the word break. Now, this is probably a clue from the examiners to just talk about breaking stress. If the force is increased by a factor of 4, you probably want your breaking stress to increase by a factor of 4 as well.
Okay, so that's really going to be coming down to looking at the ropes. And with the ropes, I suppose there's 2 things that you can do. The first one is just have more of them. So rather than just having, I think on the diagram it had 3 ropes. Well, if you want it to withstand 4 times the force, then you'd probably need to have 4 times in total the number of ropes. So you don't just have 3, you have 12.
Yeah.
Again, that's like a nice thing. You've got some numbers there. But what else can we do to the ropes to kind of really look at the kind of braking stress that they... I suppose there's going to be the same braking stress, but what can we do to the ropes?
So one of the things that we could probably do is just think about what stress is. So stress is very similar to pressure, just the amount of force per unit area. So if we wanted to increase the maximum force that they can withstand in order to keep this, let's say, constant, then we'll probably need to increase the area as well. Essentially, the thicker the ropes, the more they will be able to withstand the new force that acts on them.
Yeah, and if we basically had 4 times the force, we want that over 4 times the area. And there's this relationship again between like the thickness of the rope, which is what we tend to kind of actually talk about. So we know that the area is going to be proportional to the diameter squared, or the radius squared. So in order to make the area 4 times as big, we just need to double the thickness of those ropes. And it's kind of pretty obvious, things that need big, thick ropes, like ships and stuff like that, they need thick ropes because they're stronger. But this is kind of like the physics behind it. So I reckon, just from looking at what's on the page here, you can easily kind of pad that out to 6 marks, can't you? You've got...
Yeah, for sure.
Yeah. Any other tips about 6-marker questions?
I think probably my main tip would be to just read the question really, really carefully. So they're asking us to describe and then explain. In order to describe this, we need to do the calculations. If we were to just write a qualitative answer, we would not be taking into account the information given that the wind speed doubles.
Yeah, so I think coming away from this, if there are numbers quoted, then there's probably a good reason for that. And especially when you've doubled something like from 20 to 40, that's like a nice number. There's a reason that they've given that relatively straightforward number.
Such a good tip.
Yeah, it's not gone from like 23 to 28 and a half. It's kind of like a nice 20 to 40. That's doubled. What effects that can have. And then actually the 6-marker, break it down into bullet points. You've got some calculations. You can show that. You can then write a nice sentence just explaining what's going on. And then you've got the factors affecting maybe the shape of the tent for a couple of marks and the shape of the ropes for a couple of marks, and then you've got it.
I think additionally it's really important to actually start working on the problem even if you don't see the solution immediately, because sometimes 6 markers can be a little bit off-putting and they can almost make our brain freeze. But it's really important not to be afraid. It's probably going to be related. You know what equations describe the system. Even if you was to just write something down, the solution will probably almost jump at you as you're playing around with the equations.
So that was question 18. A difficult one on that paper. Was it harder than some of the AQA ones? I think it was a challenging question. I think actually the language was relatively straightforward and it was like a real kind of scenario. So I think that students could actually approach that. Even though they might have found it difficult and challenging, it wasn't impossible. And I think that was a fair question. Right. You like YouTube, don't you?
I do like YouTube.
Okay, the next question is about YouTube. Okay, so we both like YouTube, don't we? So this is actually a YouTube. This is, yeah, this is... But
it's what inspired the website.
Something like that, yeah. But anyway, this is just a tube in a U shape, and it's got some water in it. So this is like question 20 in the OCR paper. Again, I think students found this one fairly difficult at times. But actually, it's not that bad, I think, when you sit down and work through it stage by stage. But there's, I guess, lots of different bits of physics. So we've got, we'll come on to this in a sec, but basically we've got some water in here. We can pressurise one side, and then it can be sort of left to either oscillate or it can be sort of driven. So this question, you've got bits of sort of chemistry stuff here. I don't know what they use it for in chemistry.
I don't know.
It's just tubes and glassware. These chemists absolutely love it. But the first bit actually is to do with equations and looking at the base units on both sides. So this is really like a kind of the thing you might start doing A Level Physics with.
It also happens to be one of my favourite topics, actually, base
units.
Really? Yeah.
That's a weird topic to have your favourite. I mean, fair enough. It's all... Yeah, that's
you know what? There's with base units and dimensions, you can actually estimate the area of a black hole, which is absolutely phenomenal.
I think we'll have to do that in another video. That's
Yeah,
about
I
our
think
scope of
so,
this.
yeah.
Okay, I like the idea of that. Okay, so for this one though, we've got an equation A equals minus omega squared x, so to do with simple harmonic motion. Right, do you want to
Yeah,
show
why
how you
not?
approach this? So yeah.
So the first thing I'll probably do is just rewrite the equation. I know it's given there, but it just kind of makes everything nice and organized in my mind.
Yeah.
Okay, so the units on the left have to match the units on the right. So what are the units on the left? Acceleration, very straightforward. It's going to be meters per second squared. Now this is kind of like the tricky part of the question. Omega, that stands for angular frequency. So what are the units of that? Quite a few people might write radians per second, but the radian is not actually a base unit. The reason why that is the case, because if we think about it from maths, S is equal to r theta, the arc length. So the angle itself is going to be S divided by R. The arc length, let's say that this is S, is just measured in meters. This also is measured in meters. So the angle is actually dimensionless. Because of that, this quantity, omega, which is delta theta over delta t, will actually just have units of time raised to the power of -1.
Cool. So yeah, radians are, although we talk about radians as an angle, it's really a unitless kind of quantity. And so omega is just second to the -1.
Yep.
I suppose a bit like hertz, isn't it? Like kind of frequency is
Exactly.
things per second. Cool. Okay. So yeah. So omega squared is s to the -2.
And we've got just the final one, and x, which is the displacement, is meters, and the units on the left match the units on the right, just as they should do in physics.
Yeah, that seems a relatively straightforward 2 marks. And I think if you know this, well, not know it, but if you've done lots of practice and actually things like this are kind of easy marks you can just kind of gather at the start of the exam. Obviously, you've got to read the question, but you know that 2 marks you can get done in a minute, and that leaves you more time for the more difficult, challenging ones.
So if I was an A-level student, where could I potentially find some extra practice?
Good question. I've got a book here called The Daily Workout, which is full of questions, including actually lots and lots of questions looking at units, making sure that, can you remember the base units for lots of things? I mean, I think things like the volt, the joule, the kind of the more complicated units with like maybe 3 or 4 terms in it, and I always forget off the top of my head what are the base units for the volt.
Oh,
but
yeah.
I know I can work it out because if I know how that's related to energy and charge, or if I know what energy and how that's related to the work done and things like that, or whatever, I can work them out. But yeah, if you want to have more practice, there's plenty in this book here. Thank you for that plug. Yeah. Okay, so the next one then. This is where it gets more interesting. So we've got something that maybe students haven't done before. We've got a glass U tube connected to a gas supply. I'm just going to pressurize one side. So there we go. That's kind of what's going on here. And it does say that one end of the U tube is connected to a constant pressure. Oh, so we've got like a constant pressure in here. It's quite hard to hold. My fingers are getting sore.
Yeah, it wasn't so constant.
Yeah. And it said the displacement of the water from its equilibrium position is x, as mentioned.
So that here is just x.
Yeah. But I think the difficulty is that just as much as one side goes up, the other side goes down. So although this side might go up by 5 centimetres, that's going down by 5 centimetres, which means the difference from effectively from the peak to the trough of a wave is equal to twice that value. So 10 centimetres here. But the first one actually isn't too bad, is it?
Yeah, absolutely. Although I think there is one potential pitfall in this question is that the main formula that we're using for the pressure of a cylinder at height h doesn't come up that often in questions, but when it does, you may find it tricky to spot which formula you have to use. You typically do that once a year, and then unless you're revising well, you might not have come back to it.
I tend to say that the change in pressure is equal to rho GH.
Yep.
Sometimes they give it in a different order in like data books and things. Yep. It's the same one that's used at GCSE. If you've been doing GCSE triple science, it's exactly the same formula. Yep. And basically the pressure depends on the gravitational field strength, the height or the change in height, and the density of that fluid. And that's what it is really, isn't it?
Yeah, absolutely.
Yeah, so you put the numbers in. Density is 1,000, which is nice, times 9.81 times the height.
And I think that's the tricky part of the question, isn't it?
Yeah, because I think a lot of students saw the fact that x was 5, which was its displacement or its amplitude, but the actual change in pressure, if I go back to this, was 5 up and 5 down, so that's 10, or 0.10 metres. So that's the same as 100 times 9.81, which is just 981. Do you need a calculator for that? Am I correct? Am I?
You're absolutely correct.
Yeah, cool. Yeah, and then I'd say maybe two significant figures. I'm a bit of a stickler for significant figures. I know that's the right answer.
As every good physicist should be.
Yeah, but maybe so. Basically, two significant figures because it's two significant figures for that. Okay, here's a question. Now I don't know if you know the answer to this. If x is 5.0, that's two significant figures.
Yep.
But if you double it to 10.0, that's an appropriate way to display it.
Ooh, that's a tricky one.
So is that three significant figures?
Because I would read that as three significant figures.
Okay.
But I may be completely wrong.
It depends what you. So this is the thing where, like anything, there's like. Do you see what I mean? Because 5 centimeters is measured to the nearest millimeter, so it's 10 centimeters. So we've got the same resolution, but that one now has an extra significance in its figure, but that one doesn't.
So in this case, I would take this as 3 and this one as 2, but we always tend to use the one with the lowest number of significant figures, which in this case is 2 significant figures.
Yeah, but then they have given it to us, and the question is 3. Have I asked questions, and that's 3. That's 4 significant figures because trailing zeros add to the significance. 9.81 is 3, so really, I suppose I should give it to 981. However. I don't think you're going to get penalised if you put 981 in the mark scheme.
I would have gone for 980 personally, so there we go.
Okay, right. Well, either. Should we look at the mark scheme?
Shall we look at the mark scheme? Okay.
Right, the mark scheme. I've got it somewhere.
I'm sure that you would have gotten the marks either way.
If they're marking you incorrectly, okay, they've got 980.
Okay.
But they don't have 981 as an answer. But the main thing is, though, is that it's not 490 because it's not 5 centimetres, it's 10 centimetres. Okay, I suppose if we cared more, we could go back to the exam board and ask what they suggest. But I think we're on the right track. But that's not the main reason we're here. We're going to look at some more difficult bits. So we've now got something where the gas supply is disconnected. The water level, as we have, okay, the water level, they oscillate simple harmonic motion. So, that was close. So we've got high pressure here. When that's disconnected, it oscillates back and forwards. And actually, it's quite a lot of damping, isn't there?
Yeah, there is quite a lot.
Which is a bit more than I thought. So we'll do that one more time. And so there's some simple harmonic motion, but it's damp simple harmonic motion. So lots of bits of physics all brought together in one question. Right, do you want to do the show me question?
Yeah, sure. So it's under show me questions. So just as I'm reading this question, I'm absolutely thinking that even if I don't know how to do this, I could probably use that value later on in the next graphical question. So I think the trick is to realize that you are dealing with a standard simple harmonic motion, even though the situation is non-standard. So I have my acceleration, I have my displacement, and I can essentially compare this to A is equal to minus omega squared times x. Well, if we inspect those equations, we notice that omega is actually just going to be given, or omega squared will be, let's see, 2 rho. My rho's and g's are kind of similar, actually. Let me try a little bit harder.
That's all right. That's good. Yeah, that's good.
And then let's divide that by m, meaning that omega will just be the square root of that. But what we need now is a way of finding the time period. Luckily for us, we remember, and if we don't remember, you can use your formula booklet that omega is just 2 pi divided by the time period. Okay, let's plug this into here. So what are we going to get? 4 pi squared divided by t squared is equal to 2 rho ga divided by m. One of the things that I tend to do is to always plug in all of the numbers last. This way I'm far less likely to do a mistake. I'm not sure if that's what you do as well.
I prefer to rearrange everything. And so for something like this, I'd make T the subject. I think it's probably what you're going to do.
Yeah.
So I'd have like one mega equation with all the terms in it.
That's the mega equation.
That's the mega equation. And then I just do one kind of just do the numbers once. And that means there's less likely to be like a rounding error halfway through or something like that.
Exactly.
And again, I think with something like this, it's like nobody's ever seen that equation before doing A-level physics. So everybody finds that is different, but the skill is at realising that this is just this one over here. And therefore, the omega squared is 2 rho g A over m, which is what you did there. So yeah. So do you want to do the mega equation and work it out?
Yeah, why not?
Cool.
Always up for a mega equation. So, okay, now next question is how do we actually rearrange this? I'll probably just swap those two. Quite a lot of people might do something like cross multiplication, for instance, or I could actually, probably a slightly better approach might be just to flip everything. So I'm going to say that t squared over 4 pi squared will be equal to m, divide that by 2 rho ga. Then I'm going to bring the 4 pi kind of like up here, almost running out of space.
I think that this question, there's not much space for 3 marks, and you're starting to run out of space and you're doing it neatly and everything as it should be, but there's not much space there. I think when I did it earlier, I kind of was running out of space. So I think to get this on the page, they kind of really made that as small as they could. But yeah, it's fine. Just keep going with it.
Yeah, luckily for us, we can carry on through here. Okay, so t squared would then just be equal to m 4 pi squared. I find the most typical A-level mistake is actually just forgetting to carry out a square throughout the equation. 2 rho ga. Now I'm going to say that t is, I'm going to carry on here, the square root of this one mega equation. So our mass is 0.052. We know what 4 pi squared is. Now we have 2 times the density that was given in the that's just water, isn't it? So it's going to be 2 times 1,000.
Yeah, so again that was given on the previous page, so it's like it's easy, but information is spread across everything. When you're in the time limit of the exam, you're panicking and you're like, there's so much text to read, it is difficult.
Sure.
So I mean, yeah, I still think you should underline it or circle things. Doesn't matter if you highlight it, doesn't matter, because when they scan the exam papers in, they don't care if there's some highlighting there. As long as you can see it and it's clear to you, that's the key thing, isn't it?
I think additionally as well, if you're plugging numbers into the equation, you're thinking, I cannot solve this without that value, just kind of have a scan throughout the question. Chances are it'd probably be given somewhere in the information. But multiply by g, 9.81 on Earth, and multiply this by the area. Oh, we don't even have to calculate. Look at this. They've just given us the area. I'll find 10 to the power of minus 4, like so.
And then
some magic in the calculator.
The number for that, as you can just see here, is 1.022.
1.022.
Now, the first time I did this, I got 1.046, which I thought, oh, that's good. 1.046 is about 1. But then I realised I hadn't actually square rooted that, so that was still my value for t squared.
Ooh,
and again, this is
that's really interesting.
Yeah, so remember, like you said with squaring stuff, like remember to take the square roots, remember to square it. But yeah, 1.022 is the actual number that you would get if you worked it out. But I think that's a lot of working out there, trying to get it into a small space, and that's just, I think, the way the question was. That seemed like a lot more work for 3 marks than the first part for 2.
Absolutely.
Yeah. Okay, right. The next bit, we've got to sketch a graph. I like this. Again, if you've been using, shameless plug, my daily workout books, there's lots of times where I've asked you to draw sine curves, because I think it's a skill that everybody has to know. You'll know your teachers can do it when they do like a beautiful one on the board, but it is difficult. So this one here then, it says the oscillations of the water are slightly damped, which I think in reality it's a bit more, I mean there's like heavy, light, slightly, I mean where's one to the other, but I say that's fairly, not heavily damped, but it's not light damping, is it? Really?
Yeah, I would go on the heavier side of light damping.
Yeah, so it's a heavy, light damp. Okay, and then we need to sketch on here. So the first thing is that the period is about 1 second. Okay, so my approach would be, well, if that's 0, I'm going to say that's 1 and that's 2 seconds. Okay, so I've basically split this into like 1 second, 2 seconds. So we know the time period. The next thing is we know it's damped, and therefore over time there's going to be this exponential decay in the maximum amplitude of each kind of thing. So the approach I'd probably do to actually kind of do, because we're trying to sketch a sine graph or a cos graph in this case, or whatever it might be, and also it's going to decrease in amplitude but not time period, and I think that's the key thing. So I would do like almost like an exponential decay curve like this. I've maybe gone over the top there.
Oh, that's a really interesting approach.
So my approach would be, this is where the peak wave is going to be. I've maybe kind of done that that's a bit too much. And then it says at time t equals 0, x is 5. Can I go to the red pen?
Yep, absolutely.
So I would then go, well, at time t 0, that's 5. 1 second later, it's going to be back in the same position. So that's where it's going to be at this peak value over here. So I'm just going to put in the peaks up here. And then after another second, it's going to be something like that. On the other hand, when it's at the other side, it's going to be a bit like that. Okay, so I basically put in my maximum and minimum displacements for each cycle. And then the easy bit, or the hard bit, depending on how you like graphs, is to just kind of do the sketch of that curve. Now, it doesn't have to be perfect, does it?
No. The general shape is important, and what is important is that your amplitude should be decreasing, and also crucially that the time period should remain constant, because remember, in simple harmonic motion, the time period is actually independent of the amplitude, and this often gets tested indirectly in graphs such as these ones.
Yeah, and my approach is, I'm going to kind of have a go at doing
really
this.
Interesting.
Is I move the paper. So again, it's going to cross over the axes at these points here. So I've done like lots of I'd do this like on a light pencil. So that goes down like that. I'm always going to sort of keep my hand on the inside of the curve. Is that? Let's see. Okay, so we'll see if this works. So it's a bit like this. So hand on the inside like that. Like that.
That is a beautiful cosine curve.
It's all right, isn't it?
Yeah.
Yeah. Okay.
It's way better than I could have drawn.
No, but I think even if it's slightly like not great, I think what we're showing is, again, constant time period, decreasing amplitude, but it decreases by the same proportion each time because there's this exponential decay with the damping. Okay, so how many more times can we get the word? If we say YouTube lots, does it go higher in the YouTube search algorithm?
I think so, YouTube.
Okay, right. Let's have a look at the last part here. Mm-hmm. So this is part 3. So for part 3, it's connected to another gas supply where the pressure oscillates at a frequency of 1 hertz, which is kind of like a made-up situation. I don't know where that's happened in real life, unless you're just doing it as a demo in the lab. Explain the effect this will have on the water in the YouTube. So we can actually do this.
Yeah.
We've got a pipe here, technician attached. So Mel attached that for me and stuff. So what I can do, shall I see if I can get this working? Yeah. So about frequency of 1 hertz, so that's 1 every second. So
oh, look at that. This is resonance in action.
Yeah, so I'm only blowing a little bit each time, really. So, and it kind of builds up and builds up. So this question, it's had stuff about units. It's had something about the pressure underwater. It's had a question where you're like looking at some equations and deriving and showing something. There's a question with some graph sketching or graph drawing, where you're looking at damped motion. And now we've got resonance.
Amazing. I do love a bit of resonance.
Yeah, so this question's got a bit of everything, hasn't it? So explain the effect this will have on the water in the YouTube. So I think here, the fact we've got a number of 1 hertz, which is also linked to the fact it's got a time period of 1 second, is kind of quite nice. So naturally it oscillates with a time period of about 1 second. And now the driving frequency is very similar or the same as the natural frequency of the object. And that's the kind of, I think, the key that lots of students maybe didn't realise when they were doing this question.
Absolutely. I think the key really is to get the language really, really precise. Anytime they're asking you about why the frequency is that particular number, I would say chances are that 90% of the time it will be connected to resonance. So in this case, what we've actually calculated before was the natural frequency, which is defined as the frequency at which an object oscillates after an initial disturbance. So now we have a driving frequency that matches that. That's the exact definition of resonance. How do we word that? We've got 2 marks, so probably a couple of things to write.
Yeah, I think the fact you've got, there's like so many keywords here. You've got natural frequency, or you've got the resonant or driving frequency. And then I suppose also we want to talk about the effect it has, which it doesn't just oscillate, but actually the oscillations get bigger till they get to some maximum amplitude. So I think there's a lot of stuff there that is actually going to be quite similar to many other questions. I mean, with resonance, there's not really many things they can ask about it, are there?
Yeah, this is actually a completely side note, but I've actually seen that number in that reference before. May I borrow the cup for a second?
What's that?
May I just borrow the cup?
Yeah.
Yeah. So there's a reason why we have cup holders, actually. So the natural frequency of water is about 1 hertz, which makes it, what do you reckon the average frequency of walking is, more or less?
I suppose, 1, 2. Yeah, so I suppose
pretty close.
Yeah, about 1 hertz, isn't it?
Yeah, it's pretty close. It's somewhere within that range, which makes it incredibly likely to spill your stuff. I'll try not to draw on that paper.
But that's why there's like kind of T marks from the side from when I carried it in earlier. So yeah, there you go, more resonance in action and stuff. And you don't really think of that as a resonant frequency thing. It's like so different to like a pendulum, or a spring system just going up and down. But I think, there's so many examples in everyday life. And again, this is the kind of thing where you've got an explanation, a couple of marks available, and I think most students could get both of the marks once they've realised it's that resonant system.
Absolutely. So how would you word that question?
Oh, do you know, okay, right. So I would say that the effect of the water is that I would say that the driving frequency is the same as the natural frequency. Mm-hmm. Therefore, the system will start to resonate, leading to a very large amplitude of oscillations.
That's got to be 2 out of 2.
I think so, yeah. Right, so these questions, do you reckon they're harder or easier than AQA? Or have you not seen many AQA to compare?
I've only taught OCR, however, I have seen quite a lot of AQA questions. Oh, that's a difficult one.
Yeah, I think that these questions were tricky, but they were laid out in a very simple, clear format where students who spend lots of time revising and working had a fair chance to get all of the marks. I don't think there are any hidden marks that we wouldn't have got as teachers. Mm-hmm. I think that there have been, especially in 2023, some very difficult, challenging questions that weren't nice, as in the physics was hidden behind lots of language, lots of diagrams, and it was kind of obscured what the students actually had to do to get the marks. So I would say that these questions were easier than the AQA questions, but at the same time, they're still a bit challenging.
Yeah, I couldn't agree more.
But do you agree? Let me know in the comments. And if you'd like to see more videos, we've got some videos over on ZPhysics' channel, so you can go and subscribe there. And also we've done some other videos looking at even harder problems, like properly hard ones, with some Olympiad questions from the British Physics Olympiad. So if you want to have a look at those, make sure that you do have a look at the links around the video, and you do like and subscribe and do all that YouTube stuff. So yeah, thanks for your help. Really appreciated it. Thank you.
Thank you very much.
Thanks. Bye.